Hi, my name is Joe Osterweil. I am giving a pre-recorded talk for the 2021 annual meeting of the Society for Mathematical Psychology. And this talk is going to be about knowledge representation and retrieval, and going to be a dive into some of the one line of work that I've been doing over the last decade. So to begin, I'm going to tell you a little bit about myself, something you might not know. I actually love grocery stores and thinking about the problems that grocery stores and customers face. So outside of the just desire to have new foods and really like eating, there's another reason why I really enjoy going to grocery stores in new countries. It's one of the first places I visit, and also to my local grocery store. And that is, it's always interesting to see where people put different types of objects. So for example, basmati rice could be with the grains, where sort of the brown rice and the white rice would be held, or it might be in an international foods section if we were in the United States. And which one of those is going to depend on the expectations of your customer. So if this is in the grocery store that's mainly intended for Indian residents within the United States, then it's probably going to just be with the grains, right? Not in this international foods section. So I'm going to be using this metaphor throughout the talk, not just because I love grocery shopping, but also because it is a groundwork for understanding some ideas and theories about how people store knowledge. So just like two foods that are related are likely to be close together in the grocery store, some researchers hypothesize that knowledge representation for different types of stimuli are points in space, and being close together in that space means that those items are similar. So that's an overview of it. And generally, I've been exploring this question of how we represent, retrieve, learn, create, teach, and use common sense knowledge. So within knowledge representation and retrieval, there's three main studies I'm going to discuss today. The first is a new study that is in prep to submit, and this is that knowledge retrieval is optimal from young adulthood to young old aged. I'm excited to tell you all about that. I haven't presented it outside of small talks for specific audiences. So the second is that knowledge can be reliably estimated from fluency lists. And the third is going to be using some of these tools that we develop in the second one to analyze a disease and how it might impair different cognitive mechanisms like representation and retrieval. So without further ado, let's do this first one. And, this was not just a metaphor for the reason of that basmati rice and telling you something about me. It's also, and introducing knowledge representation, it also allows us to think about and talk about one of the main tools that people use to probe people's knowledge representation and retrieval, and that's what's called the semantic fluency task. And in this task, you might ask people for the grocery store version of it to name all the items that are in produce. However, that's not what people have done in the literature. Instead, what they've done is to ask people, among a few different other types of categories, list as many animals as you can in 60 seconds. And this is called the semantic fluency task. So adults tend to list items by category. So if they're listing these, they'll have things like wolf, and then lion, giraffe, zebra, and then dog, cat, and then horse, right? And so you can see that there's these African animals that are found in Africa that are grouped together, and then sort of domestic pets that are put together as well. it turns out that in the literature, it's sort of a robust finding that as we get older, we switch between these different categories less. So we'll spend more time in African animals and pets and not switch to others. So why is it that older adults switch less? That's what we're going to be exploring in this question. One hypothesis you might have is that, it's just due to general slowing with switch costs, right? Older adults have difficulty with switching compared to younger adults. That's something that has been found in the literature. Another one is that generally, this is sort of a slowing hypothesis, is that, things are getting slower. And so it turns out that if your rate of getting resources slows down, it's optimal to leave patches, actually, of that resource that you're gathering from at a less often. So, right, what that means is you spend more time, and it takes more time for you to switch from patch to patch. So this is, again, that adults are switching less, but they're doing so in a manner that's strategic, right? That this is not just because they're getting slower, they're switching as a consequence of the fact that they're remaining as optimal as they can be with resources that are declining. So to examine this, we did a repeated fluency study, and this is where participants come and do, among a bunch of other tasks, 3 animal fluency tasks. And we had 526 community-derived participants. This was a collaboration with Jeffrey Zemla from Syracuse University and Diane Gooding, who's another professor at UW-Madison with me. And this means that the demographics, although I don't have the distribution here, are actually very well representing, at least for Madison, Wisconsin, which is fairly still not very diverse. And we have a pretty broad range, though, of ages, which is atypical of college age, right? So we have ranging from 25 to 69 years old. And the mean age is 38.1. So returning to these two hypotheses, right? So if I think that this has to do with difficulty with switching, right, compared to younger adults, then the time that I have between categories should go up with age. However, if this has to do with just the fact that I am getting resources slower, but I'm still switching optimally, right? It's not switching per se that's the problem then. It's the problem that I'm having is it's going slower and getting to me slower, and so I should switch less often. So if I take that into account and I'm just looking at the time between these patches, then actually we should have a flat line. It shouldn't depend on age, right? That's what the sort of optimal prediction would be. So we can plot this, right? We can look at the time between categories, and I'm doing here, so if you have the time, the switching time, that's what this time between categories is. On the y-axis, bigger numbers, right, and values means that they're impaired performance or worse performance, and smaller numbers means better performance. And this x-axis is plotting this dependent on age. And what you can see is that older adults really take the same amount of time to switch categories as younger adults. Now, yes, there is a correlation of 0.04 of it taking longer as you get older, but you notice that p-value is 0.34. I just look at this and can tell us this, basically by the Osterweil or the Tukey vernacular test, as it's called, or not vernacular, the ocular test, that this is not significant. And if you want, I'm happy to send you the data to run a Bayesian hypothesis test to run for evidence for the null. It's pretty clear to me here that there's evidence that both of these are the same. So how do we actually test the optimality part in a more fine-grained way? Yet this was a prediction of it, but this doesn't tell me how close to optimal people are, actually. So to do this, we're going to do a brief foray into optimal foraging theory and think about, well, how is it that things change based on each successive animal that's said, right? So if I'm in a category, each time I say a new animal, like lion, giraffe, zebra, right, the one after that, you can see it's getting slower and slower. It's taking longer and longer to say the next item, right? So this happens to be a category switch, so not only have I then decided that I can't get anything in this category, then I have however long it takes to switch from zebra to dog, right? Excuse me. And so once that happens, it gets a lot faster. And this is consistent with patterns that people have found, and we're not the first to explore optimal foraging. There's a beautiful paper by Thomas Hills, Peter Todd, and Michael Jones on this topic that sparked a lot of inspired me to work on this. But this is looking at this with a eye to how this optimal foraging depends on the age of the person. So this is marginal values theorem. This is what tells you how to do this optimally. You should switch when the time needed to retrieve the next item in a category exceeds the global average reaction time or response time. Well, why is that, right? Well, if you have just a general average time that it takes for you to get a response, once you go above that, you're better off anywhere else than where you are currently, so you should switch. So that's, there's more rigorous proofs you can have, so why that is, but intuitively that makes sense, right? So once you're better off anywhere else, you should switch. And how you can find that time precisely, given somebody's curve for a category, the amount of time. So in the x-axis here, this is the reaction time, and the y-axis is plotting as a curve here the first item, the second item, and the third item, right? And so the x-axis here is a little bit more strange, but this is a standard within the foraging literature. But what this is plotting then on the y-axis as you get longer is the amount of time between lion and giraffe got longer, right? And the y-axis saying for time t, how many responses did I have? And the optimal rate of return you can show is when a line is tangent to this curve. So you should leave the category, right, when this line is tangent, right? And the you can prove that it's actually then the amount of space until that line intersects 0 on the negative side of the axis. I'm not going into why that precisely gives it to you here, but to give you an intuition for why this is the right one, you can see that, well, if I'm integrating something like this curve, right, that's essentially what the rate of return I'm getting is, and so this is the equivalent average as a linear, right, case. Once I go all the way over here, I'm getting more items, but I'm spending too much time doing that, right? I might as well have switched categories at that point because my rate of return has gone lower than what it was before. If I leave earlier, I'm also having a shallower rate of return, meaning that I'm getting items at a slower rate, which is less good, right? So that's why this tangent to the curve, and from a intuitive perspective, is giving me the optimal time to switch. It's when that tangent hits. Okay. So I can do this for all the data that we did, all the participants, and look at the sort of idealized optimal category leave time. Well, how do I do that? Well, I look at all the categories, I look at the curves, and then I look at when somebody should have switched, right? And I can plot that based on and compare to this y-axis, which is the average number of animals list, where I just set it to 0. Time. I start it when the first animal is said in that cluster or patch, and then you can see that the optimal time is about 7 seconds and 264 milliseconds. And the actual category leave time empirically that you get, if you calculate this based on participant responses to when they did switch, so this is the optimal category time, was just looking at the categories themselves, right? But these patches of animals, like African animals, but not looking at what happened next, right? So this is looking at what happens next and comparing the empirical case to the optimal case. And so this is really neat, right? Because this is a very, very small difference. Now, this could be due to a whole host of reasons, right? It could be that this is a wisdom of the crowds type effect, right? So, but it's still pretty shocking. I can tell you that the three of us, when we first got this result, I was certain it was a statistical artifact. And so I had poor Jeff run a lot of different ways, and I can tell you that if you're responding randomly in terms of switching categories, you definitely do not have optimal foraging. You're way far off from it, in fact. So that's already, pretty strong evidence from the aggregate, but that doesn't also tell me with respect to age, right? So what we're going to do is now do an individual level of analysis where for each participant, we've found generally their average deviance from the optimum time for them, right, to have switched from one category to the other, and see how that depends on age. And the deviance from optimum, in the case where switching gets harder, right, that mechanism is the one that's impaired by aging, then this should get larger with age. However, if switching is not impaired, then it should do so strategically, right? So what that means is that it should be flat. You shouldn't have any increase in deviance. The amount of deviance from the optimal time to switch should be the same regardless of what your age is. And so here in this x-axis, is going to be, 0 is not the sort of lowest point here, right? And 0 is the best point. So unlike the other one where higher up was better, here higher up is worse, right? And that means it's more time. Then you stayed in your cluster for longer than you should have. And below 0 means you left the cluster earlier than you should have, right? And then the x-axis again is age. And what you can see here is just broadly this very, very flat average curve, right? And this has been confirmed by running the sort of necessary statistics that this is not, there isn't a significant change here. And so this really is pretty strong evidence, and I'm still sort of shocked by how strong this is, but we've run a lot of controls, I can tell you. That's why this has been in prep for a while now, among also the pandemic being really challenging. This H2 hypothesis, it seems that this is evidence to support that switching, at least for a semantic fluency task, isn't what's getting impaired with aging. And again, this is sort of healthy aging, right? So this isn't to speak to impaired aging. But it's sort of, I think, a neat finding, because things do get slower, though, with age. And people who are older did retrieve fewer animals. Okay, so that's a really neat result. And so we might want to, though, really dive into the retrieval mechanisms a bit, but we might want to dive into these representations, right, and about knowledge. And so one of the really challenging things about representation is that there's lots of people who have their favorite representation, and it's really hard to tell which representation is better than the other. So one thing that I've been developing with Jeff Zemla over the last 5-6 years or so is a technique to reliably estimate these knowledge representation structures from fluency lists. So that's what I'm going to talk about in this second part. So how do we estimate knowledge reliably from a small number of fluency lists? Well, we first need to specify which type of knowledge representation that we're going to use. I am not saying that the one true knowledge representation for all the land and all the world and every person is semantic networks. This is just instrumental. This is to use as a utility, right, to capture and perhaps explanatory, right, to capture how somebody who's said some certain items, what their knowledge representation could look like if we assume it's a semantic network. So there are similar analyses you could do with semantic spaces. It gets a little bit trickier because the nice thing about semantic networks, as we'll see going forward, is I can really constrain the search process in a manner that's, I'm sure, possible in a spatial representation as well, but at least more challenging than for me personally. So in a semantic network, with those caveats, the way that it works is that each animal is a node, right? And nodes that are semantically similar get connected by edges. And that's why we have dog and cat, dog and wolf being directly connected, but we don't have cat and wolf being directly connected. So how do we estimate knowledge reliably from a small number of fluency lists? Well, it probably doesn't surprise you that I'm going to start with a Bayesian perspective to this, right? So what I want, right, is the best. So what do I mean by best? I mean the graph or network that has maximal probability given that I saw some semantic fluency lists X, right? So X here is a set of fluency lists. And using Bayes' rule, and since this is an argmax, I can throw out the normalization. They can break this into two separate terms, right? One term, which is the search process. That's the probability of having this all the set of lists having been said, given that this is the network that captures this person's behavior times the probability of that network, or a group of participants, and having a group network. It works in both manners. So the general strategy now that I'm going to walk you through is one, we're going to specify prior knowledge about human semantic networks to aid our inference, right? And so we'll talk about what we did with that, and that's our probability of G. We need to specify a likelihood, that other term, right? And this is a human semantic retrieval model for networks. And then once I have these two terms, it is optimization, right? I have an optimal network search problem given a set of fluency lists. So find the best matrix G that's a valid network that gives me the set of responses in the most probable manner. And then I would like to validate this empirically because I would say we're still in the infancy of validating our knowledge representation estimation techniques, and I think we need to do this a lot more than we have previously, but it takes a little bit, and you still need to publish on the way, so this is my start at doing these sorts of things. Okay, so for the prior probability, we're going to use it's a prior probability based on the exponentiated distance of the two animals in the University of South Florida Free Association database. So I can go into that more during the question phase if you're interested in it. Generally, actually, the prior, although it does help, it doesn't play that as strong as a role as you might think, as long as it's informative. So, for example, we've done this with Simon's Dedine's and others, Small World of Words data, and you get essentially the same results out. Okay, good. So that was really fast. We got rid of number one in one slide. It turns out number two is the sort of the challenging, much more challenging piece, right? So if I knew P of G given X, right, this probability of the list given people are using this network G, then I could really do this really easily. Well, let's say I knew the network, right? So one fluency list I could get then is, I could start at a random node. So I need to specify which node I start at. Let's just say I pick it at random. And so I got cat here. And then I can look at, well, what's the probability that I move from cat to dog? Well, we're going to make a very, very simplified assumption here and just say that when I am retrieving animals, what I do is, based on the node I'm at currently, I pick one of the neighbors at random. I say it if it's a valid animal and one that I had not said previously, right? So here, this is 1 out of 3 shot that I got dog. I happen to have gotten dog. And so since I haven't said that before, I move on to that. And now there's a 1/2 probability of going to wolf, 1/2 of going to cat, right? And so it happens that I go to cat, but I'm not going to say cat, right? Because this is one that I said before. Now, when we get to impaired cognition, we'll talk about relaxing that assumption and talking about the probability that you successfully censor yourself. And this is what's called a censored random walk versus the uncensored random walk, which is the underlying walk that we're doing. And then lion, and so I might get this cat, dog, lion, right? So it was a 1/3 probability. I happen to land there, and I can just keep on going on with this. And although there's work arguing back and forth about this, it captures human performance on this task reasonably well. I think that that's not a controversial statement to say. So with this, right, if I could just enumerate all the lists, then I would be good, right? Because I could just calculate then the probability of getting that list and have it based on all the different uncensored walks that would give me that censored walk, I would be good. But that's not feasible, right? Because then I have to see, well, how long did I walk around in a subgraph of my network that was all observed previously. So what we're going to do is break this into a step-by-step process and calculate this explicitly, and use some Markov chain theory to deal with this issue of the subgraph that I haven't observed yet, that I've already previously observed. So L here is looping over the product of all my lists, 1 to however many lists I have. And here I get the first one I'm assuming for free, say that it's uniform at random, and then that's basically what you have here. And then I'm looking at then the probability of saying whatever x sub n is, the next item, the second item at the beginning, given I said the previous items in the list. So how do I calculate this transition from one word to the next in the list? Well, I'm going to model each transition itself as its own random walk, and a special type of random walk, an absorbing random walk. Okay, so what this means is that I have a whole random walk that is run to then converge to just the next said word. So each transition here now is a full random walk, and I want to look at the probability that I absorb at a certain word versus another word. So previous states in this random walk I'm going to set up to be transient. So these are previous words that I've said before, or words that are not animals if I include those in my network. For the ones that we're doing here, we're always going to include animals in our, only include animals in our network. And then novel words are absorbing. Okay, so what does that look like more explicitly? So let's say I have my favorite network that I've been working with before, and I've said cat, dog, and wolf, and I'm looking at the probability that I say lion next. Well, I want to refactor my general transition matrix for this random walk then into this new one, G prime. And there, now I have 3 different, well, really 2 pieces I need to specify. The 0 and the identity matrix that's on the bottom, right? Those are kind of for free. I just need to know what the dimensions are. And then I need to know Q and R. So Q is my transition between previously seen items. So it's the matrix of transitions that connect, for example, cat, dog, and wolf here, right? So that's going to be this subgraph. If I wanted to represent a random walk on this subgraph, that's what this Q would be. R is going to be from any of these observed, any transient ones to any new ones, right? So what that means, it's the transition matrix for a random walk, right, on this network where I get one step and I'm going from cat, dog, or wolf, right, to a new animal, right? So lion, tiger, or zebra, and it turns out in this case I can't get to zebra in one step. That's going to be 0 there. And then I is the identity matrix. And so what that means is that the bottom half here is like my absorption portion, and so once I get there, I stay here forever, right? And so I'm walking around over and over again on the Q part of the graph or network until I hit the R side, and then once I do that once, I get into my absorption, and that's calculating the probability. So that ends up looking like this, actually. So it turns out the solution here is a known one for an absorbing random walk, and it's what's called a fundamental matrix, this I minus Q inverse, if that exists. Then, and it exists as long as I can get between those two nodes, right, the x of n and x of n minus 1. And then this is just looking at all the ways that I, in the last step, go from whatever step I'm currently at to the word that I end up saying. Okay. All right, start at node n, eventually get to node I, and then at step I end up going to absorb at node k, right? So we don't know what that intermediate node are, and so that's what that summation is doing. The nice thing is that this inverse matrix, this fundamental one, gets this eventually get to I. That's what that's calculating. Okay, well, how do we do this with repeats, like I said, perseverations? Well, it turns out you can do that with adding a repeat probability row emit. And again, it's the same sort of thing, except now we need to split our scene items into a slightly different thing. Absorbing scene nodes, right? Next item is a repeat, right? So that's so the Q prime now becomes, I have to take a little bit of mass away because I might repeat one of the nodes I said before, or animals, so that's that row emit parameter, and I need to give that to R, and now R has a portion, right, of these nodes from before, and its probability mass that they have is the repeat probability. It's sort of the probability you decide to emit the word, or it's the inverse of 1 minus the censoring probability, if you want to think of it that way. And then we concatenate that onto R and use the same exact math as before, and it works. Okay, so the first thing we tried was, okay, let's just use a uniform random walk, uniform prior, or the distance from USF network, both of these things. And then we can censor that random walk based on the network that I currently have. I have this list, and then I can use whatever my favorite techniques are to go backwards onto G, right, and infer that, given that. We also used this other method, and it turns out that this method ends up working really well, and especially when you have groups of participants. And what this is what's called a zero inflated beta binomial process, right, for producing a subjects graph from the group graph. So we have this group graph that's based on the same priors before, but now my probability of a subjects graph is a zero inflated beta binomial. And it turns out that we discovered this by accident. We found a heuristic that had worked, and then I stubbornly wouldn't let us continue until I could find what the sophisticated mathematical process was. And sure enough, there was one. There's not always, but sure enough, there was this zero inflated. And this comes from actually the ecology literature, because if you imagine you go to a forest and you are looking at all the animals that you saw before, and you're counting up the animals, you need to take into account that there's two reasons why you might not have seen an animal, right? One, because it's not necessarily there, or two, because you just happen to not see that animal that time, even though it's really in the forest, right? And this is an analogous thing, right? You might see an animal because it's in the network, but you just haven't gotten to it yet, and so it wasn't in that list, or because it really isn't in that participant's mind. Okay, now with those processes, I can use a optimal network search trick, right, or technique for a given set of fluency lists. And it turns out that we use a complex hand-tuned method for this which is a stochastic search with a bunch of heuristics that we developed. And if you're interested in that, I'm happy to talk a bit more about it. And we try to find the best network and retrieval parameter, and we do that jointly. And we validated this a lot to make sure that we weren't missing the optimal networks, and a lot of simulation-based work just looking at arbitrary valid semantic networks and generating lists and then estimating backwards based on our technique. Okay, so now we want to validate this empirically and compare it to other network techniques. So the validation experiment is pretty straightforward. So the first thing we did is have participants do the repeated fluency task. So we got a number of animal lists from each participant. We construct a semantic network for each participant using 7 different methods, 2 that we just defined, and then 5 other ones that have been used in the literature. And so then we curated a list of animal pairs to test the network validity. So for each of the different networks that we get from using the different methods. And we did this purposely so that we'd be able to distinguish networks based on this. So this was then another set of participants later that we tested these animal pairs with, because we had to find them with the after we made these networks. And these included pairs that are connected in all the networks, pairs that are different in at least 2 networks, and pairs that are not connected in any network. And then we had 50 participants rate the similarity of each animal pair. Okay, so if we look at that, right, rate the ones, we can break this into 2 different pieces. So each of these on the x-axis here is a different technique. So Pathfinder, which is this sophisticated technique. First edge is a technique where you just literally the first 2 animals, they have to be connected by an edge, and so you just put those together. So it takes a very long time for it to get the right network, but it converges with an as you get an infinite number of lists. So it's theoretically really nice. And then these other techniques that have been used: community networks, correlation-based networks, naive random walk. So this is where you ignore the fact that you have a censored list as opposed to an uncensored list, right? And so just treat it as an uncensored list. And then the 2 that we used. And so here we're looking at the no edge ones, right? So if each of these was giving it no edge, then these are animals that the networks are saying are not similar. So these should have a very low similarity rating, right? And that means models are doing better in that case. And what you can see here is that the hierarchical model isn't doing the best necessarily, right? And that's because it's trying to find common edges between these different participants. But you can see there's sort of a variability in performance here. The edge part here, now we want these to be bigger. I think that helps provide then these 2 together of a really nice way to understand these, right? So we want one that has a really big, value for the average similarity rating that they give to animal pairs that are linked by an edge, and a very small value to those that are not edges, right? That's what participants had given. That's what you want. And you can see that, there's a couple techniques that give you that, right? So this community network technique is a really good one. The Pathfinder is doing pretty good. Correlation-based networks, well, you have the opposite here, actually, right? It's giving participants gave higher similarity to the ones that aren't connected versus the ones that are connected. And you can see that although you invite the not hierarchical version did better for the ones that aren't connected by an edge, it did a lot better, the hierarchical one, for the ones that are connected by an edge. And we really were more focused on those edges than the no edges for the hierarchical inference, and so that's why that we got that. And there's a whole host of different trade-offs you could change with the different parameters. And just to give one example, this correlation-based network is what people often use to in the literature. Actually, it might be the most common method, unfortunately, as you can see here, it doesn't validate well. And previous work actually argued that semantic network structure for bilinguals is different than monolinguals using this technique, and in a published paper that I don't have time to talk about here, we showed that using Bayesian hypothesis testing that there's no differences between the semantic network structures of bilinguals and monolinguals, and that bilinguals are no more creative than monolinguals. Okay, so based on this, here's a giant current best practices, right? If you're interested in this, I highly recommend going to this paper, and it was in the first issue of the Computational Brain and Behavior journal. And there's also a GUI tool, and this includes actually that we've checked with actual neuropsych coders who are doing this in a clinical manner for how to code the different clusters, and it turns out that we have a very high consistency with them, although it's not perfect, for the cluster-based one that we've created, which is built off of the traditional ones, but you need to decide things like, are unicorns animals, and all sorts of things like that. So this gets into very heated discussions. I believe unicorns are animals, but Jeff didn't. Jeff won because he was the one doing the coding. So and I had to code it if unicorns were going to be animals, so I said no. That's fine. All right. So the last part of this talk is going to be about this Alzheimer's disease, using this particular tool, trying to analyze it. And it's going to try and understand these semantic impairments that have been found that seem to be somewhat inconsistent. So Alzheimer's disease patients have difficulty naming different objects. So if you show them one, ask them to say what object this is, they have trouble with it. They have difficulty categorizing animals into big and small animals. And simultaneously, so this would suggest that their semantic representations and retrieval, both, or semantic retrieval is all messed up. They actually still have semantic priming intact, right? So they're faster to read nurse when doctor was there before, when compared to nurse preceded by barn. So, and if you have matched controls, this magnitude is identical or similar. So we get two hypotheses that come out to try and explain, and neither of these completely explain these fully, right? We get a decay of semantic representation and a retrieval failure hypothesis. And both of these hypotheses are ones that were raised and still are raised in the literature on Alzheimer's, that is looking at cognitive mechanisms, and still people are trying to dissociate them, and we try to analyze that using our techniques. So you might look at, well, how does the knowledge representation, the networks that we estimate, differ, right, between those with have diagnosed with Alzheimer's and those who have not been? And we'd expect sort of breaks in edges or some difference in the edge structure, right, if there's a decay in the semantic representations. And the retrieval factor failure portion of it means that, well, their semantic representations are intact, right? They had semantic priming. How else could you have that? But really the problem is in accessing it. So this is really an executive functioning impairment. How do you actually dissociate these? There's been a lot of people that have tried designing tasks that only require representation or only require retrieval. It's really hard and possibly impossible. You can model a task that requires both representation and retrieval, and then observe whether the data are better explained by a model of impaired retrieval or impaired representation, or both, right? And that's what we're doing here. And a nice thing about using both is that we can be agnostic to which of these hypotheses is correct, because like a lot of science, it probably is going to be both. So what we need to do then is estimate semantic networks for each individual and also their retrieval parameter, right? And those are going to be our tests of hypotheses 1 and 2. And then compare the healthy versus the Alzheimer's patients. So for this, we used longitudinal data from the University of California, San Diego Alzheimer's Disease Research Center, collected between 1985 and 2016. And there were 84 normal control participants that we used. We were looking for ones that matched the Alzheimer's patients on age and other controls. and the one Alzheimer's patients that had a lot of lists. And so we ended up having about 10 lists per participant, and that ranged from 3 to 26 for the 84 normal controls that we had. And then for the Alzheimer's patients, we had about 6 per participant, and that ranged from 3 to 10 then, because unfortunately these lists, as participants get older, they only go to do this task once a year, so lasting 10 years with Alzheimer's is quite a long time. And the first thing to point out, because it's just a huge effect here, is that monitoring is impaired in Alzheimer's. This is something that we recovered with our technique, but it was something that we sort of knew was going to need to happen, right? Because we knew that there's a censoring failure in people with Alzheimer's, but once you have that censoring failure, that changes the estimation procedure. And so that's why we had to do this joint inference. And so it's nice that it actually is different, because healthy individuals, as you can see, do still make some mistakes and still perseverate. So, we estimated individual semantic networks for control and Alzheimer's, and this is just showing you a representative one from each. The control ones are much more in animals, and they look more dense, but that's actually, we'll see in a second, really a artifact of the fact that they just have a lot more animals. Okay, so the first thing we might be interested in is how many associates each concept has on average. This is the node degree, the mean node degree, and whether that differs between healthy and Alzheimer's patients. And it turns out, sure enough, Alzheimer's patients have fewer, on average, associates for each animal. So this is sort of lending itself to the impairment hypothesis that it's breaking down links. So what that means, right, is that the healthy patients have a lot more links on average for each animal. However, simultaneously, we get this sort of interesting result that is a bit different and was unexpected, right? That the edge density, so the average number of edges in our graph between nodes, is actually a lot higher for the Alzheimer's patients than the healthy patients. And so what that means is you have actually more connections, not fewer, in the Alzheimer's networks on average, right, than healthy ones. And these two things are not inconsistent with one another. This is how actually you get then that each node, right, is able to get to other nodes. And if you really want to mess up a random walk process, what's the best way to do that? Well, to have it such that a lot of the spurious associations are there, because then you're not going to find the right one. And to make sure that, this is what actually rectifies those two, is that this small world statistic value actually turns out to be a lot smaller, right? So this is this efficiency of wiring. So a random network is sort of more all over the place, and that's more what the Alzheimer's patients' networks look like, whereas a small world network is able to get between any two nodes using a random walk in a very efficient manner. So what causes semantic impairments? It turns out both, right? So that's sort of the findings that we had here. And we can capture these using the different parameters and different statistics using the techniques we had developed. Okay, so that's a set of different work and that we've done on this knowledge representation that I've been really excited to share with you. And generally this is this process that we've been doing, which is defining and deriving a normative behavior endowed with hypothesized human knowledge, comparing that to typical and atypical in some cases, right? Behavior in laboratory-based studies, prior and novelly developed ones when we need it. And now I'm sort of interested in extending this type of process to the real world, which is what takes me back to the grocery store, right? So what's something that as we get older we do spend a lot of time doing still, and that's grocery shopping. If you've ever spent time with somebody as they get older, they spend a lot of time talking about the grocery store and what they got there. And there's a lot of anecdotes about, especially with impaired cognition, going to somebody's place who had impairment and, finding that they had just gazillions amounts of Pop-Tarts because they forgot that they had already bought Pop-Tarts. They knew their grandchild was coming, and they knew that their grandchild loved Pop-Tarts, so they just kept on buying the Pop-Tarts. And so we developed this grocery fluency task. We were going to do this in person. I had these really cute bags and a logo designed for them that my partner made. And it turned out COVID hit, so we couldn't really... I have a lot of tote bags that say Wisconsin and have that cute little badger. But what we did is we did actually have an online version of this where we were able to do this where participants were submitting their grocery lists, and then 2 weeks later, they are recalling what they purchased during their grocery trips, doing this 6 times over a 3-month span. And this is as opposed to current tests being about once a year, right? So Alzheimer's happens really fast or it can happen. A decline is really fast. It also can improve at times and get worse at times. And so these kinds of once a year processes, if you're just sampling like that, you're never going to capture all that rich kinds of changes that people have when they in this particular disease. And this is the goal, is to gather enough pilot data such that we can do a much longer longitudinal study, but where we have every 2 weeks participants do this task. And we have a battery of different tests that we do at the beginning and the end as well. So this Montreal Cognitive Impairment Association, we have the Semantic Fluency task, mostly animal fluency. We have people doing an executive functioning task that's standard in the neuropsych literature, which is the Wisconsin card sorting task. We have some false memory tasks that look at things like how false memory might get affected in aging, both healthy and impaired. And we have some other pilot tests for things I'm interested in, like how fast people can recognize that a norm is appropriate, like, are you allowed to go to a beach naked or not, right? Maybe you are, maybe you're not. Okay. So the nice thing about this is it mimics a naturalistic task. Repeated testing allows for a more precise measurement of cognitive function and the ability to detect variability, even if we're sacrificing perhaps a level of noise that we get by doing this in this more open-ended fashion. And we get both semantic and episodic memory when we ask people about their grocery items. But it gets more difficult to analyze then, which is why we are then have all these other tasks to try and parcel out the different portions of it that are, mostly episodic, mostly semantic, mostly executive functioning. So, knowledge is this really pervasive and challenging and exciting topic to study. It's the one that I love to study. Not only is it essential for understanding the mind, but advances in machine learning are guaranteeing the fact that this is going to just grow in importance in society as time goes on. And one thing that I like to think about and tell people is that, really the stage we're in right now is that we as people are learning to interact with artificial agents like Siri and Alexa and Xbox and things like that, rather than agents learning to interact with us. And I'd rather that latter case. And that, I think, is also important from an equity perspective, because who has the time to learn to interact with artificial agents is the one with time on their hands. So it's really important for equity. And it also has this exciting thing that we can then test computational models of psychological theories in more ecologically valid domains by looking at the data that's in these types of models and whether endowing them with what our theories hypothesize ends up giving us better behavior. So I want to thank all the different collaborators, funding sources over the different years, many of which have gone into this, and the current and past members of my lab, and thank you all for listening.